In this lesson, I will consider systematically how to approach an NMR problem. So the following problem is typical. Given the NMR spectrum indicated on the screen and a molecular formula, C7H14O, deduce the structure of the molecule. So how do we begin? Step one, before you ever look at the NMR spectrum, look at the formula. You have some information already just from looking at the formula. Do you expect any rings or double bonds? Well, in this case, you have exactly twice as many hydrogens as you do carbons, C7H14, so that is going to suggest one ring or double bond somewhere in your structure. Okay, step two, look at how many peaks are present in the NMR spectrum. In this case, we have 2 peaks and 14 hydrogens. So that is suggesting a highly symmetric molecule. There are going to be a lot of hydrogens that are of the same type. Step 3, look at the integrals. Those are the relative areas of the 2 peaks. So in some problems, you may be given integrals in whole number ratios already, so like 6:1. In this problem, you need to take the bigger number, 65.7, and divide by the smaller number, 10.8, in order to get a 6:1 whole number ratio. Now, from looking at the integral, you know that the integral, the area under a particular peak, is proportional to the number of hydrogens in the molecule of that type. Your integral numbers in their smallest in the whole number ratio have to add up to the number of hydrogens in the molecule. So in this molecule, we have 14 hydrogens, and our integrals are adding up to 7. So what that means is we have to take both of our integral numbers, multiply them by 2 to get up to 14. So we actually know that the 2 types of hydrogen in this molecule are in a 12:2 ratio. Remember, whenever there are more than 3 hydrogens of any given type, there has to be symmetry present in the molecule. You're never going to have more than 3 hydrogens on the same carbon, so you can't have more than 3 equivalent hydrogens on the same carbon. Okay, so our structure is back up here, our spectrum, sorry, is still back up here in the top left. So step 4 is to look at the chemical shift of the peaks. So if you have IR data available, use your IR data to determine what functional groups may be present. In this case, you do not have IR data, so do your best using just the chemical shift data that you have. And what that means is you have to use the chart. Remember the chart? Proton NMR chemical shift ranges. So how exactly do we use the chart? Well, one important clue at solving NMR problems is what is not there gives you almost as much information as what is there. What do I mean by that? Well, look in the far downfield region. Well, in this spectrum, it's only blown up in the region from 1 to 3 because there is nothing further downfield than 3. So if there's nothing downfield, this molecule does not contain an aldehyde. You may ask me, well, what about a carboxylic acid? We already knew before we ever looked at the NMR spectrum that this molecule cannot contain a carboxylic acid. Why is that? Because carboxylic acids by definition contain 2 oxygens, and this molecule has only 1 oxygen. Okay, next, look in the region from 6.5 to 8.5. That's the aromatic region. Since there's nothing there in this structure, there are no aromatic rings. Third, look in the region from 4.5 to 6.5. That is the alkene region. Once again, there's nothing there, so there's no carbon-carbon double bonds, or at least no carbon-carbon double bonds that have hydrogens on them. But given that we have 14 hydrogens in this molecule, it's pretty unlikely. Okay, next, look in the region from 3 to 4.5. That's where you find hydrogens on carbons bound to electronegative elements such as oxygen, which we know that we have in the structure. Remember, you got to keep your molecular formula in mind. Otherwise, this is somewhat of a wild goose chase. Nothing there. So what that means is that the carbon bound to the oxygen has no hydrogens on it. Finally, look in the region from 2 to 3. That is the place where you would see the peaks for hydrogens alpha to carbonyl groups. Okay, so on the carbon next to a carbonyl carbon. There is a peak there. Okay, there's the septet at 2.8. So that is suggesting a carbon-oxygen double bond. So since we know that we only have one oxygen, we can't have a carboxylic acid, we can't have an ester. There's no other nitrogen in there or chlorine in there, so it's not an amide, it's not an acid chloride. We already know it's not an aldehyde because there's no aldehyde peak downfield. Therefore, our molecule must be a ketone. Okay, so while IR is a dead giveaway as to what functional groups are present, it is frequently possible to deduce much of this only from looking at the NMR data. So this septet at 2.8 integrates to 2 hydrogens. So what that means is there must be 2 hydrogens on these carbons alpha to the carbonyl group, and there have to be 2 carbons alpha to the carbonyl group because this is a ketone. So all of the remaining bonds to those 2 carbons then must be 2 carbons. Okay, so remove the ones that have to be to hydrogen and the rest have to be to carbon. Okay, so step 5, once you have enough information, which we do at this point, start constructing a structure. And this is the piece of structure that we can contribute based on the information we have so far. We have the carbon-oxygen double bond. We have 2 alpha carbons, 1 on each side, with 1 hydrogen on each of those alpha carbons, and therefore 2 more carbons have to be bound to each of those alpha carbons. Okay, so far, next step is to take stock of how many atoms you still have left to assign. Well, what have we already assigned? Believe it or not, we have assigned all 7 carbon atoms, we've assigned the oxygen atom, and we've assigned 2 of the hydrogen atoms. Therefore, to get up to 14 hydrogens, total we have to assign 12 more hydrogens. So step 7. Now we can use the splitting pattern. We did everything we've done so far without ever using the fact that we have a doublet and a septet in this molecule. So now you can use the splitting pattern to assign more hydrogens in the appropriate places. So the hydrogens that we've already assigned and included in the structure are septets. That means that there are 6 hydrogens on the adjacent carbons. And given that we have this symmetry, we basically just solve 1/2 of the molecule, and then everything's going to be multiplied by 2 for the entire molecule. So on the alpha carbon, the carbonyl carbon has no hydrogens on it. But there are 2 other adjacent carbons, and thus there are 6 positions available on those adjacent carbons that you can just add hydrogens in. So if we add 3 hydrogens to each of the remaining carbons that do not have 4 bonds, we end up with a total of 14 hydrogens, and we end up with the single correct unique structure. Bam, you're done. Almost. In most cases, you'll be done at this point. In some cases, if we're dealing with a larger molecule with more peaks, you need to repeat the previous several steps if all of your atoms have not been placed in the structure. And then finally, one of the beauties about NMR problems is that you can always check your work. If you have the correct structure written, everything is going to work out. The chemical shifts will be in the right place, the splitting pattern will be correct, and you have the right number of peaks for the number of hydrogens in your structure. So if we look at the other peak, the peak at 1.1, that's a doublet integrating to 6 hydrogens. There are 6 equivalent hydrogens on each side, so it's 12 hydrogens total if you prefer. But it's a doublet because there, on each side, there is 1 hydrogen on the adjacent carbon, namely the alpha hydrogen. And since those are CH3s at the end of a chain, we would expect them to have a chemical shift down of around 1. Okay, so that's how to attack a typical NMR problem. And in the next lesson, I'm going to go over a few cases of molecules that contain aromatic rings and some patterns and rules that you need to be aware of.